To learn more about earning college credits with study hall courses, visit gostudyhall.com or click the link in the description. I like Formula One. It's dramatic, it's fast, and it always sucks waking up on a weekend with no Grand Prix. So to fill that occasional void, let's write a really simple program that can simulate that straight line wheel-to-wheel racing that I crave. With object-oriented programming, we can model pretty much anything from the real world in code. And while we may not currently be able to fully capture the complexity of an F1 weekend, what we know about designing classes, instantiating objects, and keeping code organized will get us pretty far. Hi, I'm Sabrina Cruz, and this is Study Hall, Code and Programming for Beginners. One of the best ways to end up with a heaping mess of spaghetti code is to have a thought like, I want to write a racing simulation program, and then immediately start coding, which of course, I have never done. Doing some brainstorming before we touch any Java can help us stay organized and plan out clean code. And a great place to start is figuring out what goal we're trying to accomplish or problem we're trying to solve. Basically, we want to see which car wins the race. When we're designing an object-oriented solution to a real-world problem, how we organize our code is super important. There's a lot to keep track of in F1, but in our simplified example, let's divide the data into 3 major categories. First, we have the cars and races. These can be our objects that are defined by classes. For simplicity, we're going to focus on straight lines and ignore different track layouts. Then we can have values related to these classes, like a car's top straight line speed or a race's length. These values can be mapped to data types in Java like integers and strings. In most programs, we model these as instance variables. Then we have calculations like a car's acceleration or a race's winner. We usually model this functionality as instance methods. The organization of object-oriented programming relies on the idea of encapsulation, which is grouping together data and methods that work together somehow. Encapsulation also keeps our classes separate from each other, so there's less chance of interference and unexpected program crashes. In general, the simple things like variables and methods are encapsulated within complex things like objects. When planning out a program, it can be helpful to think about what each class of object must know, which is all of the data stored in instance variables, and what each class of object must do, which is the functionality stored in instance methods. With all that in mind, we can plan out the classes we want to create for our racing simulator. In many cases, there are multiple equally good ways to organize a program, but no matter what strategy we pick, we want clean, readable code to make debugging easy, and we want our program to be scalable over time. So we could try to pack all of the information about a race and different cars into a single class with a bunch of corresponding array list of driver names, car speeds, and so on. It's technically possible, but it would be super awkward, overcomplicated, and limit the flexibility of the program. Making a change to one specific competitor across all those lists would be a headache. Our lives would be way easier if we created 2 classes instead, a vehicle class and a race class. The vehicle class will let us create an object for each race car. We can plan to include attributes like a car's maximum acceleration, its top speed, and its driver's name. Let's also plan for some attributes to help us calculate how fast a car is going or how far a car has traveled at any given moment. Sometimes it can be tricky to know exactly what attributes you'll need in a class before you write the instance methods, but we can always go back, add, change, or delete things. That's the power and flexibility of classes. Because our vehicle class is so jam-packed with information, our race class can be fairly simple. We'll include a list of vehicle objects participating in a race, their starting position, and the total distance of the race, since we're assuming that everyone is just driving in a straight line from start to finish. All of those things will be important to help us calculate a winner. Now it's time to get coding. We'll start by defining our vehicle class based on the instance variables we planned out. These instance variables are private to help enforce the encapsulated structure of our program and keep our data organized. If we need to access them for another class later on, we'll use getter and setter methods like we talked about in episode 25. As part of defining the vehicle class, we also need a constructor method to let us instantiate new vehicle objects with specific arguments. Even though our class has 5 instance variables, we only need 3 input parameters in our constructor method: the driver name, the max acceleration, and the top speed. That's because whenever we start a new race, the current time and current speed of the car will be 0, so we can save ourselves time and effort by not typing in those values for every new object. I love being lazy and have my program do some of the work for me. Now we also need to define an instance method in our vehicle class to help us calculate and store how each car object is doing in the race. Let's pick a straightforward verb for the name, like update. As soon as the race starts, we'll need to incrementally update our vehicle's speed, position, and the total time it's been racing. To keep our speed calculation simple, we're gonna play it fast and loose with physics. Let's also assume that every driver floors it as soon as the race starts, so they immediately hit their max acceleration. To run through some example math at the beginning of the race, every car will have a speed of 0 meters per second. And if one particular car has a max acceleration of 10 meters per second squared, after 1 second it will have a speed of 10 meters per second. After 2 seconds it will have a speed of 20 meters per second, and so on until it reaches its top possible speed. At that point, the car can't go any faster, so we can add an if statement to make sure our car's current speed value can't get any higher than its top speed integer. To keep track of our car's position and time, we'll need to incrementally update those values as well. And lastly, we'll have this method return the current position of the vehicle, because that's how we'll be able to compare different vehicle objects and know when we have a winner of the race. Of course, to have a winner, we have to have a race in the first place. So let's define a race class based off our plan from earlier. We need 3 instance variables here: the list of vehicle objects that are racing each other, their starting positions, and the total distance of the race. And like any class, we'll need a constructor method to help us instantiate new race objects. We don't want to forget the original objective of our program either, simulating a bunch of vehicles speeding along a racetrack and declaring a winner. So let's create an instance method called run race to add in this functionality. To determine whether or not a car has reached the finish line, we'll use a Boolean value. At the start of each race, the Boolean will be set to false, but when any vehicle object completes the race, which we'll know because its current position will be greater than or equal to the race distance, then we'll set the Boolean to true. That's our code equivalent of waving a checkered flag. To keep track of all the cars in the race, we can set up a couple nested loops to call the update method for each vehicle in our list of competitors over and over again. All these cars will have their speeds and positions updated until one of them reaches the finish line. Finally, when the race is done, those nested loops will break, and the run race method will announce the winner with a print statement. Now that's not as exciting as a big ol' ceramic trophy. That could also break! Because we're coding an instance method in the race class right now, we need to use getter methods to access any private data from the vehicle class that we want to include in our print statement, the driver name and how much time the car took to finish the race. That's encapsulation at work. To test our program, let's create a couple vehicle objects in our main method. We can start with a tiny race between 2 cars because it'll be way easier to debug this way. We'll put these vehicle objects in an array list of competitors and then add that list to a brand new race object. Next, we'll call the run race method to let our computer simulate the race and announce the winner. Congratulations to Max Verstappen for winning. Again. This test might not have been the most exciting thing, especially since all the calculations are happening behind the scenes, so the spectacle is in our minds. But now that we have the basic structure of this program in place, we can introduce more nuances of real-life racing, like navigating a curved racetrack, or adding in pit stops, or making different vehicle objects avoid crashing into each other. We could also add some video game-style fun too, like banana peels or blue shells. Even though we had to simplify lots of the calculations in this race car simulation program, we laid the foundation for a virtual Formula 1 race or a video game like Mario Kart. And honestly, it was fun, and sometimes programming can just be fun. Organizing a program into objects that reflect the real world, or whatever rules we want, can also help our code handle big data sets, solve tricky problems, and make sure that any programmer can understand exactly what's going on. If we've chosen smart names for all of our methods, variables, and classes, our code basically just says what it does. So, now that we have all of these tools, all that's left in this series is to practice our skills and continue building intuition about what clean, object-oriented programming looks like. And that's what we're going to be working on in these last couple of episodes. If you're enjoying Study Hall, Code and Programming for Beginners, and are interested in taking an online course and earning college credit, check out GoStudyHall.com or click on the button to learn more. Thanks for watching, and see you next time.